Welcome to this guide on local deployment of large AI models for augmented reality in 2026. In this presentation, we explore how both individuals and enterprises can move from simply knowing different model types to making smart, rational deployment decisions. As AI models grow more powerful, running them locally is no longer just for research labs. With the right planning, local deployment can deliver lower latency, better privacy, and long-term cost advantages. However, hardware is expensive and fast-changing, so blind investment often leads to waste. This guide breaks the topic into model categories: hardware, logic, and practical deployment paths. Whether you are an enthusiast building a personal AI workstation or an enterprise architect planning infrastructure, the goal is the same: match the right model to the right hardware for the right purpose. Technology should serve real needs, not hype or speculation. Why do people and organizations increasingly choose local deployment instead of relying entirely on cloud APIs? The first major reason is latency. AR applications often require real-time feedback, and even small network delays can break immersion. Running models locally removes that network round trip. The second reason is data privacy and security. Sensitive design files, medical data, or internal documents may not be allowed to leave local networks. Local models ensure data never needs to be uploaded to external servers. Third is long-term cost. For heavy users, API token fees can exceed the cost of hardware over time. Finally, local deployment provides full control. You can fine-tune models, customize workflows, and integrate deeply with internal systems. These advantages do not mean cloud is obsolete, but they clearly show why local AI is becoming a strategic option rather than a niche experiment. The first model category is contextual reasoning models. These are large language models designed for conversation, question answering, summarization, and long document understanding. Examples include well-known domestic and international open models. Their key characteristic is that they are usually used for text-based inference rather than heavy media generation. That means the instantaneous compute requirement is relatively moderate, but memory bandwidth and capacity are important. These models process tokens sequentially, so system memory and VRAM size often matter more than raw peak TF. But how with blood? Because of this, contextual reasoning models are the ideal entry point for personal deployment. Even older data center GPUs or mid-range consumer GPUs can run quantized versions effectively. For many users, this category alone already covers writing assistance, coding, help, knowledge retrieval, and internal QA systems, making it the most practical starting place. The second category includes text-to-image and text-to-video generation models. Text-to-image models, such as modern diffusion-based systems, have a relatively low barrier compared to video. They can run on consumer GPUs with enough VRAM, making them popular for designers and creators. However, text-to-video is a completely different level. Generating coherent motion across dozens or hundreds of frames multiplies the computational load dramatically. Video models must maintain temporal consistency, lighting stability, and object continuity, which requires far more compute and memory. They also benefit heavily from specialized GPU features like advanced tensor cores and ray tracing acceleration. As a result, while many individuals can experiment with text-to-image locally, serious text-to-video work usually pushes into high-end or enterprise-grade hardware territory. Understanding this gap prevents unrealistic expectations when planning a local deployment. The third category is voice synthesis and dubbing models. At the lightweight end, General dubbing systems can clone voices, convert speech styles, or generate narration using relatively modest hardware. Many of these tools can run on a personal computer with a decent CPU and enough RAM. They are useful for content creators, educators, and small studios. On the professional end, however, requirements increase significantly. High-quality voice systems aim for emotional nuance, multilingual fluency, and real-time performance. These tasks often depend more on CPU multi-core performance, memory capacity, and specialized audio processing pipelines than on pure GPU power. As a result, while entry-level voice AI is accessible to individuals, enterprise-grade voice production often demands server-class machines and careful system optimization to maintain both quality and responsiveness in production environments. Multimodal fusion models form the fourth category. These systems can understand and generate across multiple data types at once, including text, images, audio, and video. In AR scenarios, such models can analyze the environment through cameras and microphones while also responding with language and visual overlays. This broad capability comes at a high cost. Multimodal models tend to have very large parameter counts and complex internal architectures. Running them efficiently often requires multiple high-end GPUs working together, large system memory, and high-speed interconnects to keep data moving between devices. Because of these requirements, true multimodal fusion at scale remains mostly within enterprises and research labs. For most individuals and small teams, it is more practical to combine several specialized models rather than trying to run a single massive multimodal system locally. The fifth category consists of industry vertical models. These are highly specialized systems, fine-tuned for specific domains such as medicine, law, finance, or industrial design. Instead of being general-purpose assistants, they are optimized to understand domain terminology, workflows, and compliance requirements. In 2026, these models are a major growth area because they can directly improve professional productivity and decision-making. However, they often come with paid licenses, restricted access, or proprietary training data. Open-source alternatives are fewer compared to general language or image models. In addition, their value depends heavily on integration with domain-specific tools and data sources. This means they are usually not suitable for general users or ordinary small businesses without a clear, focused use case and the ability to manage licensing, deployment, and ongoing updates responsibly. Choosing hardware for local deployment follows a core logic based on three decisive factors. The first is parameter scale. Larger models generally require more VRAM or system RAM just to load and run. The second factor is precision. By using quantization techniques, such as 8-bit or 4-bit weights, memory requirements can be reduced significantly, allowing bigger models to run on smaller hardware at some quality trade-off. The third factor is task type. Generation tasks like video or high-resolution image synthesis create short bursts of extremely heavy computation. In contrast, reasoning tasks often involve steady token-by-token inference, where throughput and latency matter more than peak compute. Understanding how these factors interact helps you avoid overspending on the wrong component and instead build a system balanced for your actual workload rather than theoretical maximum performance. Older data center GPUs are often called electronic waste, but they still have surprising value for certain AI tasks. Consider Tesla V100 with 16 gigabytes of VRAM as an example. By 2026 standards, its raw FP1.16 performance looks outdated compared to the newest consumer GPUs. However, many modern language models use architectural optimizations such as mixture of experts layers or more. Efficient attention mechanisms, which reduce per token compute requirements. When running inference rather than training, performance is frequently limited by memory bandwidth and capacity rather than pure compute. A 16 gigabyte card can still hold a 7 to 13 billion parameter model in quantized form. This makes such GPUs ideal for budget personal servers focused on contextual reasoning, document analysis, or internal chatbots, delivering strong value at a fraction of the cost of the latest hardware. uh, Text to video generation clearly shows the limits of older GPUs. A single short video may contain hundreds of frames, each requiring complex diffusion steps, while also maintaining motion consistency across time. This can demand roughly 100 times the compute of generating a single still image. Modern video models also rely heavily on advanced GPU features such as powerful tensor cores and hardware acceleration that older architectures lack. On cards like the V100, even if a model technically runs, you may see broken frames, unstable colors, or extremely slow rendering times. For serious video generation, newer GPUs such as high-end RTX cards or data center accelerators are usually necessary. This distinction highlights why not all AI tasks benefit equally from budget hardware and why understanding workload type is essential before purchasing equipment. Some AI tasks have special hardware thresholds that differ from mainstream language or image workloads. Professional voice synthesis is one example. High-quality, real-time voice systems often rely on strong CPU, multi-core performance, large system memory, and efficient audio processing pipelines. GPU power alone is not enough. Multimodal models represent another special case. Because they process multiple data streams simultaneously, they frequently need 2 to 4 high-end GPUs working together. Fast interconnects such as NVLink and modern PCIe standards help move large volumes of data between devices without bottlenecks. Large system memory, often 64 gigabytes or more, is also common. In certain industry verticals, proprietary accelerators may be used, but those are beyond the scope of this guide. The key point is that different model types stress different parts of the system in very different ways. For individuals or budget-conscious users, a low-cost personal setup can still be very capable. Suitable model types at this level include contextual reasoning, text-to-image generation, and general voice dubbing. A practical minimum configuration in 2026 might include a mid-range multi-core CPU, around 32 gigabytes of DDR4 memory, and a GPU such as a used data center card or a mid-range consumer model with around 12 to 16 gigabytes of VRAM. This level of hardware is often enough to run quantized language models, create images, and experiment with audio tools. Importantly, the total cost can remain within a reasonable budget. Such systems are ideal for learning, prototyping, and building personal productivity tools. They demonstrate that meaningful local AI deployment does not always require the latest flagship hardware to be useful. Enterprise or heavy-duty deployments target far more demanding workloads. These include text-to-video generation, large, multimodal fusion systems, professional voice platforms, and high-throughput batch processing. A typical configuration may involve DB Joule high-end server CPUs, 128 gigabytes or more of system memory, and one or several top-tier GPUs. In some cases, multi-GPU clusters are used to distribute large models or parallel workloads. Storage performance and network infrastructure also become more important at this scale. The lake cost is significantly higher than personal systems, and hardware prices can fluctuate due to supply and demand. For enterprises, the decision to build such infrastructure must be driven by clear business needs, predictable workloads, and long-term planning rather than excitement about new technology alone. So when does it truly make sense to deploy models? Locally, one strong reason is cost sensitivity. If your organization makes a very high volume of API calls, the cumulative token fees may exceed the amortized cost of hardware over time. Another reason is data sensitivity. Industries handling trade secrets, personal records, or government information may be restricted from sending data to external services. Efficiency is a third factor. Local systems can run continuously, support real-time AR interaction, or process large backlogs in parallel without waiting for cloud queues. For example, a powerful local setup might transcribe thousands of hours of audio in a fraction of real time. When these drivers are present together, local deployment becomes not just an option, but a strategic advantage. There are also many situations where local deployment is not the best choice. If your needs are limited to occasional document writing, brainstorming, or light research, cloud AI services are usually more convenient and cost-effective. Buying hardware in such cases often leads to underutilized machines sitting idle after the initial excitement fades. Curiosity alone is rarely a good justification for a large investment. Another major consideration is technical support. Running local AI systems involves installation, optimization, updates, and troubleshooting. Without in-house expertise or dedicated time, maintenance can become a burden. Recognizing these limits is just as important as understanding the benefits, because avoiding unnecessary hardware purchases can save both money and organizational energy. For individuals, a rational path to local deployment starts small. Begin by using cloud services or lightweight open source models to understand your real needs. Pay attention to where cloud solutions fall short, whether due to latency, cost, or data concerns. Only when a clear bottleneck appears should you consider investing in local hardware. Even then, start with a modest system that covers your current requirements. As your projects grow, upgrade gradually based on real performance limits rather than speculation. Avoid the temptation to buy a high-end machine just in case you might need it someday. This step-by-step approach reduces financial risk and ensures that each hardware upgrade delivers tangible value instead of becoming an expensive experiment. Enterprises should follow an equally structured approach, but at a larger scale. The first step is to clearly define business requirements, including workload volume, latency targets, data sensitivity, and expected return on investment. Next, conduct proof of concept tests using rented hardware or cloud GPU instances. This allows teams to measure real performance and costs before committing to capital expenditure. A careful total cost of ownership analysis should compare hardware, power, cooling, maintenance, and staffing against ongoing API fees. Only after the model choice, data, pipeline, and workload patterns are stable should procurement begin. Skipping these steps often leads to oversized systems, underused clusters, and wasted resources. Clear requirements are the foundation of rational and sustainable AI infrastructure decisions. Many hardware debates have no absolute winner. Comparing an older data center GPU to a brand new flagship consumer card only makes sense in the context of specific workloads. For some, inference tasks, memory capacity, and stability matter more than peak gaming performance. Similarly, choosing between a tower PC and a workstation depends on priorities such as upgrade flexibility, physical space, noise, and reliability. Deciding between a single powerful GPU and multiple smaller ones also depends on whether your models support ease aimed at ed. The key principle is fitness for purpose. Instead of chasing the most impressive specifications, focus on how well a system supports your actual models, data flow, and daily operations. This mindset prevents overspending and leads to more efficient, practical deployments. The core value of technology is to solve real problems, not to chase the highest performance numbers. A machine that quietly processes thousands of inferences every day supporting internal workflows may deliver more business value than a flashy system that is rarely used. In a hospital, for example, a local cluster that quickly retrieves medical knowledge within a secure network can directly improve patient care. In a design firm, a workstation that reliably assists with drafting and visualization may be more important than experimental features. Successful local deployment is measured by usefulness, reliability, and integration into daily work. When technology becomes an invisible but dependable tool, it has achieved its true purpose. To summarize, we have explored 5 major model categories, each with different hardware appetites and deployment implications. We discussed how hardware thresholds are shaped by parameter size, numerical precision, and task type. We looked at device adaptation from budget personal systems using older GPUs to enterprise, racks with multiple high-end accelerators. We examined when local deployment makes sense, driven by cost, data sensitivity, and efficiency, and when cloud solutions remain the better choice. Finally, we emphasized rational selection. Start small, test real needs, and scale only when demand justifies it. The ultimate message is simple. Technology's value lies in solving problems, not in owning the most powerful hardware. Deploy on demand, guided by purpose rather than impulse.